And in fact, yeah, so going live also takes a minute or two. So. Right. So we're live on YouTube now. The whole world can see us. I'm sure they're keen to know the latest development in relativity in Central Europe. So. Good. So I'm starting the recording too.
Fine.
And Thomas, you're the host now.
Thanks a lot, got it.
Okay, I think we can begin, right? So hi everyone, welcome to the afternoon session. And we begin with a talk by Albachiara Kogo from Tübingen on uniqueness of photon spheres. Please welcome to the screen.
Good afternoon. Can you hear me?
Yes.
Okay, perfect. So thank you for the opportunity of speaking here. I'm going to talk about my master thesis work, which was done under the supervision of Carla Zederbaum and Lorenzo Mazzieri. And it's about the theorem of uniqueness of photon spheres and more generally of equipotential photon surfaces in geometrostatic spacetime. And I'm going to use to prove it the potential theory. So let's state immediately our goal. The theorem says, roughly speaking, that if we have a geometrostatic spacetime, four-dimensional, L4G, and if we have a connected photon sphere embedded, or more generally, an equipotential photon surface embedded, then the geometrostatic spacetime must be isometric to the Schwarzschild spacetime. Okay, this theorem has actually already been proven multiple times, always adapting the black hole uniqueness proofs. So the black hole uniqueness theorem is almost the same statement, replacing photon sphere with black hole horizon. And so these adaptations were made by Zederbaum, Fehrenbach, Zederbaum and Galloway, adapting the proofs of Israel, Robinson, and Banti Masudul Alam. And what we have tried to do is to consider the potential theory developed by Agostiniani and Mazzieri and apply it to our photon sphere uniqueness. So let's fix the notation. A geometrostatic spacetime, which is our ambient, it's n+1 dimensional spacetime, such that it's standard static, which means that it's a warp product just of R and a Riemannian manifold Mg, and with word function n, which is called Laplace function. And then it's asymptotically flat, which means that this Riemannian manifold at infinity behaves like a Euclidean space. And then it is vacuum, which means that the Einstein vacuum equation is satisfied. And so the Ricci of this spacetime vanishes. And clearly the triple given by the Riemannian manifold and the Laplace function, which is called static system, uniquely identifies this spacetime. And I'm going to use the static Einstein equation then, which actually corresponds to the Einstein equation, but written only in terms of this Riemannian manifold and this Laplace function. Okay, so a specific example of geometrostatic spacetime is given by the Schwarzschild solution. Here I've just written it down to fix the notation again in Schwarzschild coordinates. So it is in fact the work product between R and this Riemannian manifold with this Riemannian metric, and the Laplace function is given by this function, and it's also involved in the Riemannian metric. Okay, now let's introduce the definition of photon surfaces and photon spheres. So a photon surface is an embedded hypersurface in our spacetime, such that it is time-like. I hope it's clear in this picture. Namely, the induced metric is still Lorentzian. And then it is null totally geodesic, which trivially means that every null geodesic that at some point is tangent to it remains tangent to it. And this corresponds to being totally umbilic inside our spacetime. And to have a physical intuition of it, it means that light, so photons, which trajectories are identified by null geodesics, are trapped into these surfaces. Okay, and a specific case of photon surface is given by the equipotential one, which means that if we consider this sigma surface and -1 dimensional, which is given by the intersection of the photon sphere and the Riemannian manifold mg, which foliates the spacetime at some fixed time t, then okay, in the picture is represented by this red line. Okay, so this sigma here is such that the lapse function is constant on each connected component of it. And if the lapse function is constant regardless of the time we are fixing, so actually on the whole photon sphere, or better in every connected component of it, then we have a photon sphere. Okay, and here I just draw the photon sphere in Schwarzschild to give an intuition. So the photon sphere in the Schwarzschild in 3 dimensions occurs at r equal 3m in Schwarzschild coordinates, and it's slightly above the black hole horizon, which occurs at r equal to m. And in the whole space-time, it can be imagined as a cylinder where, okay, the light is trapped. Okay, so finally, I'm going to talk briefly about potential theory, which is the tool that I'm going to use to prove the uniqueness. So this theory just takes Riemannian manifold mg0 and a smooth function n, such that the Riemannian manifold is asymptotically flat, and this triple satisfies these conditions. The first two ones are the PDEs that corresponds to the Einstein equation, and they are the static Einstein equations, and they are actually written in terms of the Riemannian manifold. So the tensors of the Riemannian manifold and connection of the Riemannian manifold and the Laplace Beltrami operator of the Riemannian manifold, and the lapse function, which more generally is called static potential. And then we want this smooth function n to, we just take it such that at the boundary of m attains this value n0 between 0 and 1. And at infinity behaves like this. So it goes to 1. And the first approximation is given by this m, which is called mass parameter, and actually corresponds to the eigenmass of this system. Okay, so in this setup, Agostiniani and Mazzieri in their potential theory papers just took started from this function, which is u1, which is a function of s that goes from n0 to 1 and identifies the level sets of n across our Riemannian manifold mg, and it's given by the integral of over a level set of the norm of the gradient of n. And clearly, since by the second static Einstein equation, our n is harmonic, this function is constant, so it doesn't depend on the level set we are considering, and it holds for any static system. And it actually has this value, which is the value at infinity, and involves the mass parameter and the volume of the n-1 dimensional sphere. So they started from this observation and they generalized this idea to any p bigger or equal than 1, taking these UP functions, which are given again by a function and an integral over a level set of the norm of the gradient of n to the power p. So in this case, apart from the case p equal 1, at infinity, we still have this behavior, this value as a limit, involving again the mass parameter and the volume of the n-1 sphere, but they are a priori not constant on each level set. It only happens in the Schwarzschild spacetime. So somehow these functions can be used to detect whether we are dealing with Schwarzschild or not. And in fact, this is written rigorously in this theorem, which says that for P slightly less, for every P slightly bigger than this optimal value, which is slightly less than 2, our UP functions are differentiable, and the derivative is always non-positive, which means that the UP functions are non-increasing somehow along the level sets of n, and also this let's see that this derivative involves again an integral over a level set of an integrand function that involves the norm of the gradient of n and the mean curvature of our level set. And in the rigidity case, so if this derivative is 0 at some level set, which must not be the 0 one, because otherwise this is trivially 0, so it doesn't give any information. So if it's in the rigidity case, we have it implies that we have the isometry to the Schwarzschild solution. So in order to apply this, we want to apply this theorem for our uniqueness result, and so we want to prove that having a photon sphere, or more generally an equipotential photon surface, we actually are in the rigidity case. So let's observe that to be in the rigidity case, so here to have 0 equals 0, we just have to impose that this integrand is less or equal than 0, because here we have a minus some positive quantity. And this is true. I mean, a sufficient condition for that is just that this inequality holds almost everywhere, which means that the quantity in the brackets here is less or equal than 0 almost everywhere with respect to the Austin measure on some level set of n. So now the easiest way to try to prove it is just to take the value of the Laps function on our equipotential photon surface at some time and see if it's satisfied, and then we can conclude. And in fact, using the properties of equipotential photon surfaces, which are the following, we are able to rewrite this sufficient condition in a very easy way, just imposing a lower bound on the Laps function, on the value of the Laps function on the equipotential photon surface. So these equipotential photon surfaces are such that if we consider their intersection at a time slice, okay, this sigma, the resulting sigma, is such that it has a constant mean curvature inside the Riemannian manifold, and also the normal derivative of the Laps function with respect to the outward normal in this Riemannian manifold is also constant, and it's related to this constant value of the mean curvature h and the value of the Laps function, which is also constant again on the equipotential photon surface, via this identity, which involves a parameter c. This parameter c actually identifies somehow the type of equipotential photon surface that we are considering. And in dimension 3, if it's equal to 3/2, we have a photon sphere, which is just a specific case of it. And then finally, we have also that the scalar curvature is constant, and it's related to the mean curvature by this identity. So we are going to use these identities to rewrite the previous sufficient condition to be in the rigidity case, and it gives just this inequality, so this lower bound for n0. And in dimension 3, it corresponds to this right-hand side 1/√2c, and of course in photon spheres it's just 1/√3, which is in fact the value of the Laps function on the Schwarzschild photon sphere that I drew before, that we have seen before, yes. So, okay, we are only left to prove this lower bound for n0 to conclude, and we can still use potential theory and observe that since the UP functions are non-increasing along the level sets of n, the UP functions computed at n0 have a bigger value than the value at infinity. And this rewritten in terms of the property of equipotential photon surfaces and playing with this inequality somehow, we get this lower bound for n0 with which involve this b, and b is this quantity here, which is written in terms of constants and this parameter c, and but more precisely in terms of this integral over a level set of the scalar curvature. So somehow to have a precise bound here, we need to bound the integral of the scalar curvature. And this is possible, of course, in dimension 3 using Gauss-Bonnet, since it's possible to prove that actually the photon sphere is actually a topological sphere. Okay, so we can still use Gauss-Bonnet and find an upper bound for this integral and actually get what we wanted and conclude. But okay, we have to work first of all in dimension 3, because in higher dimension we have no analogous to the Gauss-Bonnet theorem, and also we have to impose that this level set, so the equipotential photon surface, has only one connected component. And because if we assume, for example, a k is the number of connected components that we assume at the beginning, for example, then we get this bound on the right hand, this value on the right hand side, still using Gauss-Bonnet under some assumptions. And this is strictly less than the value that we want to attain, so we cannot conclude. And okay, and these two observations are what I'm going to point out at the end, because okay, as I said at the beginning, there were other proofs of this theorem, and in fact the Banting-Masood-Ulam and the Zederbaum and Galloway adaptation didn't assume the photon sphere to be connected, or the equipotential photon surface to be connected, which was the case in this proof. But it also, I mean, it was a good way to prove it somehow, because we avoided the assumption of regular foliation by hand, which is a big deal somehow. And also we avoided to use the positive mass theorem, which was used by them. And it's a very strong result somehow. Okay, so these are my references, main references, and thank you for your attention. I'm here for any questions.
Thank you for your talk. So it's time for questions.
Piotr, may I ask a simple question related to the definitions? Because I missed something about this photon sphere. So there was this photon surface. It is of codimension 2 or for codimension 1? This is crucial, yes? So on this picture, this is the hypersurface of codimension 1, yes?
The pink one, yes.
Yes. And then
yeah.
And then you assume that this is not totally geodesic, but null totally geodesic, yes, which is less than totally geodesic. So this means that the part of the extrinsic curvature vanishes. Which part of the extrinsic curvature vanishes?
So
for null totally geodesic.
So it can be proven that it's this being null totally geodesic is equivalent to be totally umbilic. So
because
somehow
totally geodesic surface means that the full extrinsic curvature vanishes. That the geodesic internally and the geodesic in the ambient space is the same geodesic. But here maybe you assume that when you start with a null, so in some sense on this surface there should be null directions, yes? It cannot be space-like. This free space in classical 4 dimensions. So
it is time-like. So
I try to recognize because because there is another surface which is better known is how do you say it in English? Non-expanding horizon, yes, and then the full extrinsic curvature vanishes, and this is null surface. So I try to understand this hypersurface. What is the signature of the metric?
No, so the signature is, so it's a Lorentzian metric on the surface. It's not null.
Okay.
Because it's the first condition.
So this is time-like, yes?
Yes, it's time-like.
Okay.
This is the first condition. And then if we consider, I mean, taking a null geodesic in the ambient space, then it's also a geodesic in our photon surface.
Okay, so okay, I understand this definition, but can you transfer this definition to the extrinsic curvature condition? This is my question. That some component, maybe this null component of extrinsic curvature vanishes, or something like that.
So you mean the mean? So okay, yes.
So the full tensor. So roughly the derivative of this Lorentzian metric in transverse direction to the surface.
So you mean the second fundamental form?
Extrinsic curvature.
Yeah, the second fundamental form.
Yes.
You are asking. Yes. So the second fundamental form is pure trace. So it can be written as the mean curvature over the dimension of the hypersurface, so over n, times the induced metric. And actually, yes, and actually it's positive, the mean curvature.
So this is so the extrinsic curvature is proportional to the metric?
Yes.
Okay.
Yes. I mean, I can give you also the reference of this proof, but it's actually, I mean, stating that it's time-like and not geodesic is equivalent to say that it's totally umbilic. So the second fundamental form of the extrinsic curvature, it depends on the name you give it to it, is a multiple of the metric. Yes.
Okay. Thank you very much. Okay.
Okay. So we still have time for one question.
If I may, can you hear me?
Sure.
Okay, yes. So you mentioned that your proof has some advantages over the other ones because you're making less assumptions somewhere. So what would be the optimal statement then?
Without one connected component, because the optimal statement is removing this connectedness. And in fact, Sederbaum and Galloway did it, but they had to use the positive mass theorem. I didn't use it.
So if you remove it, you get a clean statement. There's no need to. There is no. I mean, it's a nice technique what you've done, so it's very interesting. But so they already have the optimal theorem now for this problem.
Yes. In fact, at the beginning, yes. Actually, yes. And also they proved it in higher dimensions. But okay, somehow we tried to see if with this technique maybe it was possible to. And
yes, of course, it's always interesting to have new proofs.
Because it was really a technique which was really topological and somehow using very strong other strong theorems. Yes.
Okay.
Thank you very much.
Thank you very much for your talk. So it's time for the next talk. The next talk is by Leo Bigorn. The next talk is by Leo Bigorn from Cambridge on decay estimates for the massless Wassermann equation on the Schwarzschild. Please, Leo.
Hello. So is it good? Are you seeing,
Can you share the screen? Oh, yeah.
Yeah. And I should put full screen probably. Okay, is it good for you?
It's fine. Yeah, go
Ah,
ahead.
Okay. So first of all, thank you very much for the invitation. So my talk will concern decay estimates for the massless Vlasov equation on the exterior of Schwarzschild black holes. So in order to give some motivation, let me start by saying a few words about the Einstein-Vlasov system. So these equations are used in order to model collisionless particles of mass m, for which we neglect all interactions except gravitation. So more precisely, the solution is a Lorentzian manifold with a Lorentzian metric and the velocity distribution function of the particles. And we have first the Einstein equations, where on the right-hand side, we have the energy momentum tensor of the Vlasov field, and the Vlasov equation, which is a transport equation. So the evolution of the particles are described in phase space. And more precisely, the Vlasov field is defined on a subset of the cotangent bundle, which is often called the mass shell, and which is defined by this set. So it is, of course, completely equivalent to define it on the tangent bundle, but I found it more convenient in order to see the analogies with the wave equation to define it on the cotangent bundle. Again, in this talk, we will study massless particles. So the mass m is equal to 0, and the mass shell is the bundle of the future light quants. And what we can say is that the Vlasov equation reflects the fact that the particles are following null geodesics. So maybe one main open problem concerning this system is the nonlinear stability of the subextremal Kerr black holes. And the first step in order to say something about this problem would be to study the asymptotic properties of the solution to the massless Vlasov equation on a fixed Schwarzschild background. So this means that we completely forget about the Einstein equations and we only study the massless Vlasov equation where the metric here is fixed and is the metric of Schwarzschild spacetime. So there was only one work on that topic, which is the one of Lars Andersen, Peter Blue, and Jeremy Joudiou, where they obtain an integrated energy decay estimate for slowly rotating Kerr spacetimes. But the thing is that their estimate does not provide a good control of the solution near the event horizon and near the trapped null geodesics. So one of my goals was to prove on Schwarzschild an estimate which give a good control of the solution near the event horizon and near the trapped null geodesics. And moreover, I wanted to prove Conway's decay estimates for the components of the energy momentum tensor of the Vlasov field, which is something that they did not obtain. So the main idea of the proof is to use vector fields method. And for this reason, I found it convenient to recall the main elements of vector field method for Vlasov field on Minkowski spacetime. So in that case, the Vlasov operator is much easier to write, and it reflects the fact that the particles are moving along straight lines. So vector fields methods are well known for being a robust method in order to obtain decay estimates for the wave equations and Vlasov equations, at least on Minkowski spacetime. Okay, and the method was developed by Klein-Norman for the wave equations a long time ago. But for the Vlasov equation, this was developed more recently by David Feynman, Jeremy Joudiou, and Jacques Smoulevici. So the main ideas are the following. So first, we need a set of commutators, which are vector fields, which reflect the symmetries of the equation. So in the case of the massless Vlasov equation, these commutators, so the vector field which commute with the Vlasov operator, are the complete lift of the conformal Killing vector field of Minkowski spacetime. So we do not need to know in detail what is the complete lift, but the thing is that we take the conformal Killing vector field of Minkowski, and we add a similar part in V. Okay, so the Tx part of these commutators are exactly the same as the initial conformal Killing vector field. Then we also use constants of motion, which are weights defined on a phase space, and which are preserved along the null geodesics, so that they are solution to the massless Vlasov equation. In order to obtain a uniform bound on the solution, we can use the fact that the L1 norm of the solution is preserved in time, and we can use the good properties of the constants of motion and the commutators in order to propagate weighted L1 norm of the solution and its derivatives. And using that together with weighted Sobolev inequalities, which are often called Klein-Norman-Sobolev inequalities, we can obtain pointwise decay estimates for the solution. So maybe an important remark is that since the commutation vector field for the wave equation and for the Vlasov equation have the same part in Tx, these two methods are compatible, which means that we can apply both of them in order to study the solution to a system of wave equation coupled with a Vlasov equation. And it led to the stability, to proof of stability of Minkowski spacetime for the massive and the massless Einstein-Vlasov system. Okay, so now we can start by studying the massless Vlasov equation on the exterior of Schwarzschild spacetime. And I will start by saying what are the difficulties compared to the case of Minkowski. So first, the set of the commutators is much smaller. So here we can only commute with the complete lift of the stationary Killing field dt and the complete lift of the rotations. So the problem concerning the constants of motion is quite similar. We only have the t component of the velocity vector and its angular part. As in Minkowski, we have a conservation law which arises from the fact that dt is a Killing vector field. Okay, so we can prove boundedness for L1 norm of the solution, where here the integrand, which is the contraction of the energy momentum tensor by dt and the unit normal vector field of the foliation. So this quantity is an energy density, which is in particular positive. But the problem, compared to the case of Minkowski, is that dt is null on the event horizon. And the consequence is that the energy density here degenerates near the event horizon so that it doesn't control all the components of the energy momentum tensor. So the control over the solution given by this conservation law is not good close to the event horizon. Next, if we want to prove pointwise decay estimate using Sobolev inequality, something that we need to control is the L1 norm of the radial derivative of the solution. And the thing is that in contrast with the case of Minkowski, we do not have a direct control of the radial derivative of f in L1. And finally, there are trapped null geodesics on Schwarzschild at the photosphere. But the fact that these orbits are unstable leads to dispersion so that we can prove decay estimates. But it is well known that, for instance, for the wave equation, in order to estimate the solution near the photosphere, we need to lose regularity. So here we will see that we will need to lose something as well. And maybe the last question. So in Minkowski, we obtain time decay on the solution by using the fact that we can commute the equation by commutators with weight in t. And here, the commutators does not have weight in t. So the question is how to obtain time decay using vector field method. So for this, one way to do that is to adapt the RP weighted energy method of Dafermos and Roniansky. So this method has been used many times in order to study the wave equation on black holes. And here I had to adapt it to massless Vlasov equation. So the key elements of this method are the following. So first, we need to use an adapted foliation, a foliation which is adapted to the radiative property of massless Vlasov fields. So more precisely, we will consider hyperboloidal foliation or space-like null foliation, which join the future event horizon to future null infinity. So like that, we will be able to prove decay estimates for the energy flux through the foliation. And the reason is the following. So the energy flux through sigma tau here does not measure the energy radiated to null infinity and inside the black hole between time 0 and time tau. And this has to be compared with a foliation by t equal constant hypersurfaces, where the energy flux through these hypersurfaces are preserved in time. So we cannot prove decay estimate using for the energy flux through t equal constant hypersurfaces. So we also need to prove a uniform bound for a non-degenerate energy norm. So this means that we need to improve the energy estimate that we obtain by using dt as a multiplier. And we also need a non-degenerate integrated local energy decay estimate. So on Minkowski space-time, it will be an estimate of the following form. So this means that we need to obtain a bound on a space-time integral over a domain which is bounded in space. And finally, we need to prove and exploit a hierarchy of R-weighted estimates in the faraway region, so for large R. And for instance, if we start by p equal 1, we would obtain an estimate on a space-time integral of f over a region of large R, which is bounded by a weighted initial norm of f. And by putting everything together, we can prove decay estimates for the energy flux of f through the foliation. And the main idea of the method is to transform spatial decay into time decay without using commutators and multipliers with weight in time. Okay, so finally, in this last slide, I will briefly give you the main ideas in order to prove, to obtain all the estimates required for using the RP energy method. So for this, we use well-chosen vector fields as multiplier. And in fact, we will need a more general process. But the idea is to use a vector field as a multiplier, and so that the error term in the energy estimate will have a good sign. Like that, we will be able to estimate a space-time integral with a positive integral. So for instance, for the uniform bound in time for a non-degenerate energy norm, what we can do is to use the redshift vector field and Dafermos and Roniansky. And the thing is that, in fact, the future event horizon is a very favorable place in order to estimate the solutions. For the integrated local energy decay estimate, we can use a radial vector field as a multiplier. So in the language of the Vlasov field, this corresponds to using a weight of the following form here. So a function of r time the radial component of the velocity covector. But here, by doing such a thing, we obtain an integrated local energy decay estimate with a degeneracy near the photosphere. And in order to improve the control, so near the photosphere, we need to use a weight which is more general, which is not obtained by using a vector field as a multiplier. And by working a little bit, we can prove the following estimate. So we estimate the space-time integral that we wanted to estimate by the initial L1 norm of f plus a weighted LS norm of f, where S can be arbitrarily close to 1. And the thing is that in the case of the wave equation, we had to lose regularity. Here we need to lose some decay in V. We need to assume more decay in V on the initial data in order to control the space-time integral here. And finally, for the hierarchy of RP-weighted estimates in the faraway region, we can use the weights of the form RP times the outgoing component of the velocity covector with an exponent q, which satisfy the following condition. And by putting everything together, what we can prove is arbitrary decay for the energy flux of F through the foliation. And more precisely, if we start the hierarchy with Rp here, with P, we can prove decay as 1 over tau to the P. And finally, let me briefly explain you how to obtain the Pontoise decay estimate. So the main issue is that in contrast with the case of the wave equation, we do not have a direct control of the L1 norm of the radial derivative of F. So here the idea is to use the massless Vlasov equation here in order to control the following quantity here. So we can control the radial derivative of the velocity average of F multiplied by the square of the radial component of the velocity vector. And after that, we can control the most important component of the energy momentum tensor. So by contracting it by n twice, where n is the strictly timeless vector field. So we can control this quantity by a Holder inequality, by a weighted L1 norm in V of VR square times Fs, where S is an exponent larger than 3. And since F to the S is solution to the massless Vlasov equation, we can apply what we did previously in order to estimate the main component of the energy momentum tensor by a decay rate here, which can be arbitrary, where the decay in time can be arbitrarily fast. And well, I think that I have just finished, so thank you very much for your attention.
Thank you very much for an interesting talk. Are there any questions?
I will have a question. Leo, can you hear me?
Yeah.
Okay. So I was just wondering, the last thing you just mentioned, this F to the S, this exponent. Can you briefly say what how this helps to take S higher? Then this looks very interesting to me. Can you comment on this? What the benefit of this is? Where this enters?
Yeah. So the thing is that so I can estimate pointwise the velocity average when there is the VR star square here. So the thing is that if you look, for instance, at the velocity average with VT square, what we would like to do is to force VR square to appear. And for this, I make an Holder inequality. And I need for this to take S larger than 3. So you apply a Holder inequality, and in one integral, you do not have F. You have 1 over VR with a small exponent. And in order to be sure that this integral is finite, on the other one, you need to take S larger than 3.
Okay, thanks a lot. Thanks, Leo.
Okay, so I hope that it was clear, but it just comes from a Holder inequality.
Well, I get the idea. I get the idea. Thanks a lot, Leo.
So, may I ask something?
Sure.
Okay, so you're saying the rate can be arbitrarily fast, but surely the initial data will prevent you for this to be arbitrarily fast. So what governs a threshold for the decay rate?
Yeah, so I mean, if you start by the RP energy method by P, I mean, then you cannot prove a better decay than 1 over tau to the P. So you need, if you want to prove a decay as the following decay rate, 1 over tau to the P, you need to assume that
the initial data have a finite norm with this rate. Okay. Yeah, exactly. Okay, great. So if they're compactly supported, is compact support preserved in this case? I have no feeling for this, but
I think that compact supported would be preserved in time. So for compact supported initial data, you could really prove arbitrary decay.
And you get a uniform estimate too. Okay.
Right. Yeah.
Okay. Thank you.
I have a question. I guess, well, it's clear that this cannot work for massive Vlasov because you have stationary solutions. But does it mean that that you would expect some instability for massive Vlasov on Schwarzschild?
Right, yeah, I think that there is a result of Olivier Sarbar about that. He proved that, yeah, there is a stationary solution, I think, because of the structure of the trapping, which is more complicated. I think that the trapping is stable, so you cannot prove such decay result for the massive case. Okay. So that I think that the Kerr family would not be stable for the massive Einstein-Vlasov system.
Mm-hmm. Are there any further questions?
So what would happen then if it's not stable? What will happen with the solution?
So I cannot say for sure, but probably that I mean there are some solution to the massive Einstein-Vlasov system with a non-vanishing Vlasov field which are close to Schwarzschild. So you could expect when you perturb a Kerr black hole for the massive Einstein-Vlasov system to converge to such a solution.
And the Schwarzschild ones are known to be stable, or?
I don't think that they would be stable. Yeah.
David, do you know anything about it, or is this something that you're looking at with Maciek Maliborski numerically, or?
No. But I know that so Jacques' student Fatima, she will give a seminar in the Matter conference next in 2 weeks. So she has this, I think, this result that you can, what Leo just I think mentioned, that you can go arbitrarily close to Schwarzschild with massive solutions. So that means that so if you perturb, I can just repeat what Leo said. So if you perturb, you will pick one of those solutions, and this is a static solution, and so you will not. So Schwarzschild will not be stable in that sense, but one of those solutions may be. But there's no rigorous result on any stability, even in spherical symmetry of those solutions, because that's very hard at the moment, at least.
Okay, I think it's time to move on. Thank you very much. And the next speaker is Liam Urban from Vienna. He will speak about blow-up of waves on Friedmann, Lemaitre, Robertson, Walker spacetimes. Please welcome to the screen, Liam.
All right, can you see everything?
Yes.
Perfect. Just going to quickly set a timer so don't go too much over time.
Yeah, go ahead. Yeah. So yeah, we are 5 minutes late. Yeah.
All right, so thank you everyone for the invitation to allow me to speak today. I'm going to present the work I've been doing together with David Feynman here at the University of Vienna on the blurb of FLRW space waves on FLRW spacetimes as part of my master thesis. So just as a quick outline, I'll give a quick recap on physical relevance and the general setting on FLRW spacetimes, although of course Zoe Wyatt already gave that to an extent, thankfully enough, yesterday. Then I'll quickly introduce our setting since it's not 100% standard for the FLRW case. Take a quick detour into general results regarding nonlinear stability of Big Bang formation on FLRW spacetimes and how that relates to our results. Then I'll introduce our results and go through the individual proof steps to finally give an outlook on where we're going to go from there. So again, I'll try not to repeat too much, but on a large scale, we assume and perceive the universe to be spatially homogeneous and isotropic up to small perturbations. Again, the well-known picture of the cosmic microwave background is a strong indication that this is a very fair cosmological assumption, and also the way that superclusters are spread out throughout the universe as a whole is also more or less consistent with this assumption. Purely from this, Robertson and Walker proved all the way back in the 50s or 60s, I believe, that this already forces the metrics to be FLRW metrics, so that we have some time on the one hand, on the other hand, spatial time expanding of three-dimensional manifold of constant sectional curvature. So either flat surface, sphere, or hyperboloid sheet. The question one has, of course, okay, we perceive now the universe is roughly consistent with an FLRW picture on large scales. Back with the cosmic microwave background, we perceive something similar-ish up to small perturbations. So the question is, does that work all the way back towards the Big Bang, or was there some other universe close to the Big Bang that then just happened to fall into something close to FLRW spacetimes? So the more mathematical question to that is the Big Bang formation non-linearly stable with the FLRW background or near FLRW background? And the first step towards this is to study the behavior of waves as a toy model for the linearization of this perturbation. Moving on to our setting, we precisely look at four-dimensional spacetime with signified R component for the time and a compact three-dimensional manifold without boundary for space, and then look at something which looks precisely like an FLRW spacetime with this Riemannian metric G bar. And we look at the expansion rate for the case of cosmological constant 0, so t to the power 4/3 gamma, with gamma between 2/3 and 2. I'll comment in a second on those two boundaries. And then we look at solutions to the wave equation on these spacetimes. The one point where we aren't, strictly speaking, FLRW spacetimes, but something more general is, again, that we aren't assuming that this metric or that the space we're looking at is of constant sectional curvature. Of course, every case of that type is contained here, but we realized while we were working on the proof that it was completely irrelevant, besides maybe some slight nicer constants, that we assumed constant sectional curvature. So we just dropped it in the proof and look at this mathematically more general case, although the physically relevant cases are just the classical FLRW spacetimes, as far as I'm aware. And again, to comment on the edge cases, in the case of gamma equals 2, we are in the Einstein-stiff universe. So if this basically models the expansion of a massless ideal fluid universe, then in this massless ideal fluid, the speed of the sound is the speed of light. And on the lower bound for gamma, this corresponds precisely to the Milne universe. And we expect that to be a special case because the Riemannian curvature tensor simply doesn't blow up in the space in the Milne universe. So we also don't expect any kind of wave blow up along similar veins. To a quick detour on what general results on linear and nonlinear stabilities over this background are. Speck proved in one paper on its own and one together with Dotniansky back in 2018. On the one hand, that the Einstein scalar field system is globally nonlinearly stable over spaces of positive curvature with regards to this near FLRW background. And on the other hand, for the flat case, we also have a result for the stiff case that we absolutely can't quite handle. But the moral of the story is one has results for certain types of curvature or certain types of expansion, but not in our more general setting. So then in the same year, Franzen et al. Looked at what is basically our setting. So again, the expansion rate t to the power 4/3 gamma, and excluding the stiff case and excluding the Milne universe, and then looked at the blurb of waves within the flat FLRW spacetimes as the specific restriction, whilst we then look at the more general class. And they proved a general blurb result, which roughly sketched and is also along similar veins what we then managed to prove in more generality. They proved that the blurb would be of the form basically when the waves go back towards the Big Bang, the waves roughly look like some smooth prefactor times t to the power 1 - 2 over gamma. I'll remark in a second on where this comes from, but that's basically the idea. And the one point where they used the nicety of being in Euclidean space essentially is that it allowed a law of that this allowed them to commute any spatial derivative with the wave operator, simply because all spatial derivatives commute. So a lot of technical estimates became significantly easier, and in particular, it was fairly easy to use any energy estimate on the wave to any derivative of the wave, and thus gets the regularity of the leading coefficient fairly easily. For our setting, we're going to need some kind of replacement for that, obviously, since we can't commute derivatives. However, this comes very naturally when we look at what the wave operator actually is in our general setting. Namely, it is this kind of splitting into time derivatives up to order 2 and a scaled spatial Laplacian, where the Laplacian, I really denote the Laplacian on this space m bar, which is in no way adapted to the expansion. This power t to the power 4/3 gamma, this factor in front, is precisely from the expansion of the space in our spacetime. In particular, this Laplacian is completely time independent, so we can just commute this Laplacian with a time derivative acting on a scalar wave. So we can, instead of having individual derivatives commuting with the wave operator, we now just have the Laplacian commuting with the wave operator, since, of course, the Laplacian also commutes with itself and it doesn't act on any time prefactor at all. And this basically is the replacement we have to make and then try to go through the argument in total. Second remark, what one can see from this simple expression is precisely why we expect this blurb rate of 1 - 2 over gamma when we go towards the Big Bang, which is that if we look at a spatially homogeneous solution, so when the Laplacian becomes 0, this really just reduces to an ODE of second order in time. And one that is even very trivially solvable precisely by t to the power 1 minus 2 over gamma. So one expect in this case that any blurb will be similar to this spatially homogeneous solution unless something really weird were going on. And that is precisely what we proved. Vaguely stated, I'll go into more specifics during the rest of the talk. Our result is that when we follow waves back towards the Big Bang, we precisely have the same asymptotic expression as Franz Nadal proved in the Euclidean case, that we have a smooth leading coefficient A times this spatially homogeneous solution plus some higher order terms. And that if we give some initial conditions on the initial data at some slice t0, that we can also actually prove that we have precisely this rate of blurb towards the Big Bang. Of course, for example, the 0 function would also technically be a wave, but doesn't experience blurb, obviously. So we do need some kind of additional requirements. Good. The main technical ingredient, what we used, which is to an extent in a way almost similar in model to what we just had in the K-estimates for Schwarzschild space terms, was that we need some kind of energy that we have to control. In particular, we used the energy that is the most intuitive when we compare to the standard wave equation in, like, not even space-time, just as one would do in the standard PDE course, where the L2 norm of the time derivative and the L2 norm of the spatial derivative is actually truly conserved. In our case, we look at the L2 norm of the time derivative of a wave and the L2 norm of the gradient rescaled by the expansion rate. So basically, this is just the homogeneous H1 norm on our spacetime, only that we integrate this entire thing not over some adapted surface, but really over just the spatial manifold without any further adaptation. Exactly. Again, comparing this energy and inserting what we expect to be the blurb order. In this spatial part would obviously vanish, and here one would have something of the order t to the minus 4 over gamma. So one would expect that when one rescales it for what we expect to be the blurb rate, that this would stay bounded, and this is precisely what we prove. That we can, from our initial data set at some point of time t0, comparing backwards, we can control with this rescaled energy any rescaled energy at earlier times. And the same type of estimate holds when we rescale the energy by what we suspect to be the leading coefficient, only that, of course, we have to adapt the order a bit. The basic idea here is really just a Grunwald estimate, which is fairly easily calculable. We really just use the closest of the manifold to integrate by parts and the form of the wave equation. Although there is another proof that was done in Franz et al., which we could also adapt here, similarly using energy flux methods. Next, again, we use the idea that we can just commute the Laplacian and the wave operator, that we can just generalize any estimate we got on our wave to any Laplacian of the wave. So we really get something that looks like very high somewhat of regularity, just that we're skipping a lot of derivative orders and that we run some technical issues. But the basic moral idea is that we can, with these energies, bound very high order derivatives of both our wave and our wave rescaled by what we suspect to be the leading order. With these technical estimates already in the bag, we can now move on to the first step of the blurb result, namely that this leading coefficient A actually exists, that then also is leading order immediately follows from the energy estimates, and that when we take the difference, then we actually do have a convergence in this rescaled energy, which really proves that we have strictly this leading order A times our homogeneous solution plus something of higher order, which by comparison vanishes at least. The proof itself is lots of half technical. The basic idea is that using the energy estimates from earlier on the rescaled wave, we can prove that in particular, the time derivative of this rescaled wave is something that is integrable in an L1 sense. And then one can just use the fundamental theorem of calculus to extend our rescaled wave from T0 all the way back to the Big Bang. Again, just fundamental theorem of calculus. And we just copy and copy this procedure for any order Laplacian. So we have a lot and a lot and a lot of limits. And we have to show that these limits are consistent to then obtain smoothness. And this is really just some stubble of machinery that's rather tedious to calculate through. The basic idea and real key technical ingredient is that on closed manifolds, as we had before, the Laplacian is an elliptic operator in space. And with that, one can just get a lot of very clean stubble of estimations and Yeah, that is really essentially the basic idea. And this is where we really keenly need the closeness. Without it, this wouldn't quite work. Finally, we have to give some kind of conditions, as mentioned before, on that this is actually the leading order of blob. I have the precise formulation on the final slide if anyone's interested, but morally, we have to require 3 things, or it's sufficient to require 3 things, to be more precise. Number 1, that at where we take our initial data, the time derivative is not identical to 0. This is more or less to just exclude stuff like constant solutions or zeros. Secondly, that the point at which we take our initial data is small enough compared to the blur rate. Essentially, this is that a certain prefactor is non-negative, and this is a relation of some constant dependent only on gamma times an exponent of t0. And actually satisfying the smallness becomes significantly harder the more we move towards both our edge cases. So the method we have right now can't quite cover these edge cases of the stiff universe and the Milne universe. Third condition is that, which basically already contains the first in a way, but this makes it slightly more specific, is that the L2 norm of our time derivative must, in some sufficient way, control both the L2 norm of its own Laplacian and up to 3 derivatives of spatial L2 data. So even slightly more generally, we have to control up to 3 derivatives in both space and time in an L2 sense, with the first time derivative in an L2 sense. If all of these 3 things are satisfied, then we prove that, then we can prove that the L2 norm of our leading coefficient over space doesn't vanish, well, it's strictly positive, and thus, by continuity or just in general, we have that globally, we have some kind of blurb of strictly this leading order 1 minus 2 over gamma. Finally, since of course, for, well, applications, so to speak, and actually being able to check these kind of conditions, having data on the entire manifold isn't particularly useful. One would be interested in whether one can require some kind to get some similar conditions for local data. This is currently still a work in progress on my end. The basic technical difficulty is that a lot of this global blurb results use integration by parts and in an energy flux method that I mentioned before in passing. And if we go to some kind of smaller domain, we get first order derivatives, which of course, by the entire way we structured up this proof, we've always skipped so far. We always went from 0 derivatives to the Laplacian spatial derivatives and so on and so forth. So we need to get some kind of way of controlling some first order derivatives. But we highly expect that very similar conditions can be set on a local set to then give some kind of local blurb. Maybe these might be a little cleaner when we go to strictly spaces of constant sectional curvature. Where can one go from there? As I mentioned before, the entire end goal to an extent is that we can then attack nonlinear stability just with this intuition in mind of what happens with linear perturbations, considering this toy case. And in particular, the interesting case is negatively curved spatial manifold, simply because we just don't know anything there, or know the least there, more precisely. Another way that we can go with this is, again, that just using this to the Milne universe probably won't yield too great results if we consider the massless case, because again, the Riemann curvature tensor just doesn't blow up, so we don't expect anything to happen. But we do suspect that if we add some kind of matter fields to this entire universe, that this may be able to then actually still generate a type of plurbs, and so we are considering throwing this entire procedure essentially to the Milne universe with some matter field added. And finally, we are also considering applying this to other types of equations. Again, we had this in the talk previously, that there are some conservation laws in the Einstein-Plato system, and whether this entire idea of using conservation laws to then generate smoothness and stability results, if it can be applied to other equations, is of course of interest, and we will consider looking into that. All right, that's it for me. Thank you for listening, and I'm open to questions.
Thank you very much. Thank you very much for a very clear presentation. So, questions?
Do you know anything about what's happening in the expanding direction?
So you mean with positive cosmological constant, or
no time going, because
with future
going to 0.
I know of the Milne universe case that we have proved that there is a pseudo nonlinear stability that I think both David and someone else's name says me proved that kind of stability result. I don't know future stability in our setting necessarily. Maybe David knows more on that than I do.
I would suspect they're all stable to the future, but I'll think about this and tell you, Piotr, in next week.
So one way of trying to get a non-linear model out of this would be to allow the metric to depend upon time slightly, because that's what, well of course, if you are in the blow-up regime, then and the metric depends upon the fields, the dependence will not be slight. But I imagine that in this energy method, there is room, right, for a slight or for some time dependence. Maybe it would be interesting to see how bad it can go.
I think that there is quite a lot of room for energy dependence because, again, looking at like the thing that really drives the blow up in our case is this time derivative part. The spatial part is basically just a technical nuisance for the energy conservation. So given if we have at least something similar to this this wave operator expansion, maybe up to some additional perturbations, given that, I very strongly assume that one could then expand this because, again, the time derivative is really the only thing one has to control effectively.
Maybe even if you had some terms which blow up in the metric, but at a slower rate than this conformal factor, then you'd be able to do something, and that would be a starting
one point where that might be a
start.
little bit of a difficulty is that precisely in this rescaled energy, that is where the blur rate of the energy is precisely this spatial coefficient. So one has to be a bit careful maybe expanding there because that's right on the edge of still working essentially. But I think that with that adding time perturbation into the metric should, with a little more work, lead to the correct result, like just intuitively.
Okay, thank you. Thank you all three speakers of these sessions. I think we should take a 5-minute break. So let's meet again at 3:10.
Hi, Bobby. How are you?
Hi. How are you? Fine.
Okay. Yeah. Enjoying the conference. It's been going pretty well so far. So.
Yeah.
A lot of interesting talks by.
Yeah.
Young people.
Hello, Robert.
Hello. Hi.
Thomas.
Yeah.
Should I just stop the video screening and restart in 5 minutes, or we just run?
I would say you should just keep it running, because in the first talk today in this afternoon session, when you started also, you had to be host, and when you recorded, it was according to Zoom servers, which prevented me from recording locally. So I think it's like this.
Okay, so let's just leave it running. And
that's better. Okay.
Good. Maybe someone else can try to record as a backup. Jacek, can you record?
No, I cannot.
Has anyone a big, well, yeah, a lot of memory and try to
That
record?
was going to be my remark. Actually, I think that would need lots of space, and since I'm on a laptop.
It's about 1 giga per hour.
More.
You don't trust my backup, or do you?
Well, somehow it would be nice to have a backup. Because we don't have a recording button now, so it looks like maybe we're not recording at all.
At the moment, I'm not recording. I'm starting the recording for every session separate, so for every talk separately.
So the private talk is not recorded.
But it's live on YouTube.
It's only on YouTube. Yeah.
No. Well, that's even better.
So Bobby, you have you're the boss, right?
Yeah.
So you have to tell us when we start.
You have to switch on the microphone.
You have to switch on your microphone.
Okay. Yeah, sure. No, in 2 minutes.
Yeah.
Good.
Bobby, if you open the list of participants, you will see if people are raising a hand. So Thomas can switch them on, but you need to say, I'm allowing this person to speak or something like that. So keep the list of participants open, and if you see a raised hand, then you.
But then it will cover part of your screen. That's the problem, yeah? You won't see the files properly. That was my problem, at least. So, Herbert, did you get your coffee? Ah, yeah, I see.
I just fetched me some coffee, yeah. But unfortunately, it seems that the acoustic problem still is present.
My acoustic problem, yeah?
Yes, there are interruptions in when you are talking.
I don't know. It's probably a problem with the transmission.
So I think we should start. Can everybody hear me?
Yes.
I can hear you.
So hello, everybody. Welcome to the second half of this afternoon session. We'll have 3 talks as always. Philip Ficek, are you here? I cannot see you.
Yes, hello.
Can you share your screen?
I'm trying to do it right now. And I guess...
Wonderful.
Good.
Great.
Okay. Okay.
So, hello again. So first talk is by Philip Ficek from Krakow on stability of stationary solutions of nonlinear Schrödinger equations. Please go ahead.
Thank you. So hello, I'm from Jagiellonian University, where I'm a PhD student under the supervision of Piotr Bizon. And in this short talk, I would like to present our results connected to my PhD thesis. And at the first sight, maybe the topic of this talk seems not very fitting to the topic of this conference. So let me start with giving you some motivation why I am interested in Schrödinger, nonlinear Schrödinger equations. And in particular, even that the topic is pretty general, I will focus exclusively on one kind of nonlinear Schrödinger equation, which we called SNH system. And I will begin by showing motivation to tackle this problem coming from general relativity. Then I will say a few words about existence and uniqueness of stationary solutions of this system. And I will finish with the main focus of this speech, which is stability of such solutions. So to give some motivation, one of the most important probably problems of modern mathematical relativity is anti-de Sitter spacetime stability. And there are lots of numerical evidence connected to this problem, but not so many proofs or analytic results. So to better understand this difficult problem, we decided to tackle the simpler version of it, which is a non-relativistic limit of perturbations of anti-de Sitter spacetime. And the idea is pretty simple. We take Einstein equations, and with a negative cosmological constant, we put some scalar field onto this spacetime. We write down the equations, and then we assume that the scalar field is weak, so we can put some ansatzes. And when we put these ansatzes, we write down the equations. We can expand these equations in the powers of 1 over the speed of light. And then we may perform the limit with c going to infinity, but with one important point here, that lambda in this limit is not constant, but it goes to 0, but in such a way that this combination, lambda times c squared, goes to some finite negative value. And having this in mind, we go to this limit, and then it turns out that in the first order of 1 over c, we obtain such equations. This is pretty messy because of the existence of physical constants we wanted for the sake of this expansion. So let me just change the units, and this is our final equation, or the system of equations. So we called it Schrödinger-Newton-Hooke equation as a pun name, but it is also can be met in literature as Hartree equation or as Schrödinger-Poisson equation, and it has many names. And one can see that the lower equation is just the Poisson equation, so we can integrate it and obtain more compact equation, a single one. And of course, now the name is pretty visible because we have the Schrödinger part, we have the nonlinearity, which looks like self-gravitation, hence the Newton, and we have harmonic trapping, hence Hooke. And this equation pops out in plasma physics, in solid state physics, and it's pretty well investigated. So we now see that it is also motivated by general relativity and by ADS stability problem. And it turns out that if one is interested in this equation in other dimensions than 3 or 2, which are typical dimensions for quantum mechanics, there are not many results, where more precisely there are results up to dimension 5, but for higher dimensions, there are almost no results considering this equation. The reason for this fact is that 6 is the critical dimension, energy critical dimension for this equation. So all of the typical methods used for dealing with such problems based on variational methods break down there, because needed theorems from functional analysis don't work in supercritical dimensions in this case. And hence there are no mathematical results. And also it wasn't very interesting from physical point of view, because if this is a Schrödinger equation, it's rather interesting to consider in 3 dimensions. But as I showed, there is now some motivation coming from GR to tackle this problem. So we wanted to understand better the dynamics of this problem in dimensions 6 and higher. So let me start. If we want to understand the dynamics, we have to start with the bases, which are, for example, stationary states. So let me start with existence of such states. So we take our equation, we just put typical ansatz for stationary state, and we also simplify our lives by considering only spherically symmetric solutions. It may look like a big loss of generality, but in fact, it turns out that this equation, for this equation can be shown that the ground states, which are most important stationary states for us, must be spherically symmetric. So in fact, if we focus on ground states, there is absolutely no loss of symmetry, no loss of generality when restricting ourselves to spherical symmetry. So in fact, we have these 2 equations, and now we want to discuss the existence of its solutions. So let me spell out what I mean by this existence. So we have these 2 equations for U, which is our field, and V, which takes the form of potential. And the question we are posing is that we want to find solutions with such boundary conditions. Of course, derivatives of U and V has to be 0 in the center due to spherical symmetry. We also want these 2 functions to go to 0 in infinity. And we want to have some control over the U. So let B denote the central field value, like the value of U in the 0. And the question is, if we take some arbitrary B, do there exist values of omega in this equation such that the solutions of this equation satisfy the boundary conditions? And it turns out that the answer is yes, and it can be shown in supercritical dimensions using shooting methods, so basic ODEs and dynamical system methods. That for every B, for every central value of the field, there exists an infinite ladder of numbers, omega 0, omega 1, omega 2, etc., such that for omega n, there is a solution of these equations satisfying these boundary conditions. And in this solution, U crosses the 0 exactly n times. So we have just the ladder of excited states, and in the beginning of it, it's omega 0. It is a value, a frequency of the ground state. For every B, we can give such a values. And we can show even more that if we are talking about ground state, for every B, there is just and only one omega zeros giving us this ground state, so giving us a positive solution. Hence, we can define a function omega of B. And this is just a function which takes the value of the field in the center and gives us the frequency of the ground state having this value in the center. And let us see some plots of this function. So for example, for the critical dimension, d equal to 6, we can see that this function starts at omega equal to 6, which we could suspect since it is for low values of B, it is almost typical linear quantum oscillator. So it has frequency of ground state equal to 6. But then as B goes higher, the omega goes lower, and we can see that this is just a decreasing function. More interesting situation happens in supercritical dimension, because then we can see that this is no longer decreasing function, but rather oscillating. And the interesting fact that can be seen from this plot is also that there exists an infinite number of different ground states admitting the same frequency, which is this frequency denoted by a dashed line. And if we go to higher dimensions, we have the same situation. For example, in dimension 15, we also can see such oscillations, but the higher is the dimension, the smaller is the amplitude of these oscillations. So we have to zoom in very close to see these oscillations in this case. But then something surprising happens. In dimension 16, these oscillations vanish. And again, omega of B happens to be a decreasing function. And then in dimension 17 and so on, the situation is the same. So it looks like we obtain these oscillations at dimension 7, and then we are losing them in dimension 16. And so this is pretty interesting result. And as we will see, these dimensions 15 and 16 will come back soon. And now, when we established some knowledge about existence of the stationary states, let me talk about the stability, and I will focus on stability of ground states. So it will be simpler to use this one-line version of the equations to consider the stability. And the approach is pretty typical. Let U be a ground state of frequency omega, and then we put such an ansatz where f and g are some small real functions, and we are looking at the dynamics of f and g. And after putting this ansatz into this equation, then simplifying everything, and then giving the real part and writing separately the real part and imaginary part of the obtained equations, we get these two equations. And I would like to point out two things. At first thing is that as we can see in the upper equation, on the left-hand side, we can see that it tells us about the evolution of the function f, but on the right-hand side, there is only function g present, and vice versa. In the lower equation, we can see that g and f also are only on the one side of the equation. And the second fact is that the upper equation, even though it looks pretty ugly because of this integral part, is in fact this integral is in fact just a function because u is a fixed ground state, so we can calculate it, and it's a normal. What we have on the right-hand side of the upper equation is the normal linear local differential operator. On the other hand, the lower equation has f function inside the integral, so even though it's still linear operator, it's now non-local, so it needs a little bit. We need to be a little bit more careful with calculating some stuff connected to it, and we can also rewrite these equations in more compact matrix form, where L minus and L plus are just these linear operators defined by the first and the second equation. And what we want to do is to use this L minus and L plus to investigate the stability of this ground state. And we will do it using the Vakitov-Kolokov criterion. And to present it, I need some notions. So let me introduce N of omega, which is mass of solution U, which this is a solution to frequency omega. It is just a mass as a L2 form, L2 norm, sorry. And the other notion is that if L is a linear operator, let N of L be the number of negative eigenvalues of this operator. And having these two things in mind, we can formulate the Vakitov-Kolokov criterion, which says that if we have some ground state of frequency omega, and if then changing this frequency of this ground state changes the mass of the solution in a way that the derivative is negative. And then additionally, if for this solution L plus has, operator L plus has exactly one negative eigenvalue and L minus has no negative eigenvalues, then the solution is spectrally or linearly stable. And now I could say a little more about this criterion and how well our system satisfies it. For example, the third criterion is always satisfied because our operator is positively defined. And one can show, for example, also that analytically that for small values of B, so small central field values, all these criterions are satisfied, but instead I would like to show some numerical results. And I'm sorry, they may look pretty rough, but they are just, they are very early results, and they literally were prepared yesterday and today. But the main gist, I think, is visible from them. So let me focus on the first line, which shows 3 plots connected to this criteria for the dimension 7, which is the first supercritical dimension. We can see a beautiful spiral as a plot of mass versus omega. This spiral is parameterized by values of B. When omega is equal to 7, the B is equal to 0, and then the B is getting larger and larger along this spiral. And we can see that initially, indeed, the slope is negative. So the first criterion is satisfied. But then we have a maximum, after which the slope becomes positive. So in this part, it seems that solution is not stable. But then again, there is a part where it might be possible that the solution is stable again, because again, the slope is negative. So we have to check the other criterion. And it looks out that it turns out that in the meantime, one of the eigenvalues of L plus operator changed its value to negative. So even though that here we have positive negative slope once again, the function this one state is no longer stable because the other criteria are not satisfied, and hence we can see that there is a stability only for some interval of values of B from 0 to some fixed value, which is this maximum here.
A question?
Yes, of course.
Is this criterion if and only if? In other words, I mean, you can use it for stability, but can you also use it for instability if it fails, it's unstable?
Yes, as I understand, yes, it is equivalence. Now we can move to dimension 15, and now it is not visible because of the scale of this plot, but also there exists a very tiny spiral in this case. And in fact, the situation is qualitatively the same as in dimension 7. We can see that also close to B equal to 10 to the power of 4, we have a change of the sign of one of the eigenvalues of L plus. So we also have the same situation that for small values of B, there is relatively small, of course, there is stability, but then it is lost and never regained. But again, the situation changes for dimension 16. Then we have no spiral structure. It is just this plain decreasing curve. And also the values, the eigenvalues of L plus operator don't change at all. Like there is always one negative eigenvalue and all the others are positive. And so this is an interesting observation that in dimension 16, we suddenly obtain the gain of stability, like all the ground states become stable in dimension 16 and higher. And in summary, as we could see, Schrödinger equation, or this particular nonlinear Schrödinger equation can be obtained also on the grounds of general relativity, and it gives us some motivation to consider it in higher dimensions, even in supercritical dimensions where not much is known. And there are two specific dimensions where the situation changes radically. The first one is the critical dimension, and it was already known knowledge that one has to, for example, use other tools to tackle this problem in higher dimension than 6, and that the results may be, of course, different than in subcritical and critical dimensions. But the new surprising fact is that there is another, maybe not critical, but important dimension, which is 16, in which also behavior of this system changes drastically. And among the other changes, one of the most important is that all ground states are becoming stable for arbitrarily large values of B in these dimensions. And this is still a next step in understanding the full path, which is understanding the dynamics of this approximation of ADS problem. So the next step will be performing some simulations of dynamics of this system. So that's all, and thank you for your attention.
Thank you very much. With little time for some questions or remarks.
I have a question.
Yes, Martina, please.
So this is only for the ground state, right? Do you have any idea what happens to the excited states, or is there anything interesting at this dimension?
Well, as for excited state, I have done some numerical work, and it looks like the situation, I don't know yet about the stability, because we cannot use this criterion for the excited states, and it is a little bit more complicated there. But as other things, for example, the shapes of these functions omega of B or this n of omega are exactly the same. They are just a little bit shifted, but qualitatively they are the same. But also we don't have, for example, results of uniqueness of these excited states, because in general, uniqueness of excited states is a very difficult problem.
Okay, thank you very much. Thanks again for a clear talk. So we'll move on to the second one.
Bobby, there is a question in the from the participants. Charles Robson.
Sorry, where?
And so maybe you go ahead and speak. You have to unmute yourself, Robson. Yeah.
Okay. Hi. Can you hear me?
Yes.
Hi.
Yes.
Okay. Good. I was just going to ask. Do you know if any of the equations that you study are integrable? So do you know if maybe for any value of D, value of any parameter, if the systems are integrable? So maybe you'd have.
Okay, well, I was studying here just this one particular equation, and it is not integrable, but in principle, the same ideas can be used to other types, like Gross-Pitayevsky, for example. But I didn't, I haven't been checking any completely integrable equation, so I don't know.
Okay, thank you.
There's also a question in the Q&A. Philip, do you want to open the Q&A and
okay.
answer it live?
The sequence of frequencies of some results. It's a good question. No, I don't know. I have no idea.
Sorry, I didn't hear the last question.
Okay. Okay.
It's the questions. If you click on the Q&A tab, you'll find it.
Sorry?
maybe I read it, right? Do you know of some results?
It's in, I see.
On how the frequencies are distributed.
Okay, so as I said, I have no idea about some methodic like way to say where these frequencies lay, other than numerics.
But isn't there a Weil asymptotic formula or something like that?
Yeah, okay. There is a asymptotic formula. Okay, that exists. That's right. But okay, but it's only asymptotic. And also one can use bifurcation theory to show for the small values of B. But okay, so yes, so sorry, you are right.
May I ask a question also, Bobby?
Sure, yes. One last question.
There is this mysterious way of passing to the limit with lambda, right? So lambda goes to 0, but in a specific way. Is there any feeling why that's the right thing to do? Or
yes, well, from the simplest and maybe not very enlightening point of view, it's if we take any other limit, the one term in our equation will either vanish, and then we have like Minkowski instead of anti-de Sitter, or it blows up. So we have to take it like this, but there is more deep reasoning behind this. There is a paper by Gary Gibbons from 2003 where he shows that this limit must be do this way to preserve the full 10-dimensional family of symmetries of the space-time. Without it, if we do it otherwise, we may lose the Galilean invariance.
Robert, okay. May I ask a simple question?
The very last question.
The very last one. You presented some L plus, L minus operators, which were just ordinary differential second order operators on a half axis, as I understand, yes?
Yes.
Roughly. Because this is spherical symmetry, or this is general?
Well, this is general, but we can constrain ourselves to spherical symmetry.
So this is on the half axis, yes?
Yes.
And the problem is, what are the boundary conditions for those F and G's? Because operators should need boundary conditions if you want to examine spectra, yes?
Sure. So for the function f and g, the boundary conditions are that they must vanish in infinity. They must have vanishing derivative in 0, and I guess that's all.
Okay. So mixed boundary Dirichlet, yeah.
Yeah.
Neumann-Dirichlet.
Neumann-Dirichlet. Yeah.
Okay.
Okay. So now we should really move on to the next talk, which is given by Mariusz Łączea from the AEI.
Hi.
Hi. Can we see your screen, please?
Yes, I think so. Just a second. Yes, I think it's, I hope it's working, right?
Wonderful. Okay, so welcome, Mariusz. So you will speak about the spin Hall effects and the localization of massless spinning particles, please.
Very much for the introduction. So my talk is going to be based on work that we did here at the AEI in the geometry and gravitation group, together with Lars Henderson, Jeremy Jodiot, and some other collaborators as well. Okay, so while the title might not suggest it, my talk is mainly going to focus around the propagation of light in curved spacetime, and I hope I'm going to convince you about this in a moment. Okay, so let's start with some basic facts. So in general relativity, the propagation of electromagnetic waves is often considered using the geometrical optics approximation for Maxwell's equation. And what we get from this approximation is that light rays follow the null geodesics of the underlying spacetime. And we use this approximation to make most of our astrophysical predictions. Okay, but now the problem is that geometrical optics is valid only in the limit of infinitely high frequencies, and we know that the radiation that we observe is a finite frequency. So then there is the question if we can do better than this, if we can come up with a better theoretical model for describing the propagation of light in space-time. Okay, and my goal today will be to present to you such a model where we are going beyond the geometrical optics approximation by including higher order corrections. And in this case, what we obtain is propagation, that the propagation of electromagnetic waves becomes polarization dependent. And
I have a question here. What exactly do you call geometrical optics? Is this just geodesics, or you're thinking about iconal expansions, or what's
it's just the geodesics.
Thanks.
Okay. And this is what we considered in the papers mentioned over here. So extensions of geometrical optics for Maxwell and linearized gravity. And by doing this, we obtain the following. So the dynamics of polarized wave packets is effectively described by massless spinning particles. And these particles deviate from the usual null geodesics that we have in geometric optics. And just to give you a feeling of what this effect looks like, let me give you a very brief example. So here, we consider a Schwarzschild black hole, and we consider here some source of radiation far away from the black hole. And now if we emit a null geodesics from this source of radiation, we see that the null geodesic will remain in the equatorial plane of the Schwarzschild black hole, and we will get the ordinary light bending for null geodesics. Now, on the other hand, if we consider the equations that we obtained and we consider circularly polarized light, and we do the same, we look at similar trajectories, what we will get is that due to the polarization, this light rays will get deflected off the equatorial plane, and in the end, we'll have this finite deflection angle off of the equatorial plane of the null geodesic. And this also will depend on the state of polarization of light. So this is basically the spin Hall effect of light in Schwarzschild in a nutshell. Okay, let me go on. So another important point that I want to emphasize over here is that the energy centroid of polarized wave packets, or in our effective description, the position of massless spinning particles is observer dependent. And this effect comes into our equation of motion and plays a very important role. Before going further, let me tell you a bit more about this observer dependence of the energy centroid of wave packets. And I'm going to start this with using a simple mechanical model. So for example, here, I'm considering a spinning wheel, which is located in the XY plane, and the angular momentum is directed along the Z-axis. And on the left, I have an observer which is at rest with respect to the axis of the wheel. And this is how the observer sees the wheel here on the left. And now, on the other hand, if I boost this observer with some velocity along the x-axis, what the observer will see is presented over here. So the wheel gets contracted along the x-axis. And furthermore, because the wheel is rotating, the energy center of the wheel gets shifted along the y-axis. So the observer will not see the energy center at the center of the wheel, but it will see it displaced along the y-axis over here, depending on the rotation of the wheel. Okay, so now we can extrapolate this classical model, and we can replace the wheel by an electromagnetic wave. In particular, we can replace the wheel by a circularly polarized Gaussian beam. Here, what we see here on the left is the 0,0 component of the energy momentum tensor for such a circularly polarized Gaussian beam propagating in the Z direction, as seen by one observer. So we see that it is perfectly symmetric in this case, and the energy centroid will be at the center of the XY plane. And now the question is, what happens when we boost this observer along the x-axis? So the boosted observer will see a deformed image like over here. But most importantly, the boosted observer will see the energy centroid of the Gaussian wave packet shifted along the y-axis, depending on the state of polarization of the beam. And this polarization dependent displacement, delta y, is called the Wigner translation. So more about this can be found, for example, in this paper or in many other papers in the literature. Okay, so with this in mind,
sorry, only a remark. Is this only true for me? But I cannot see the bottom lines. So the references you are referring to do not show up on the screen.
I don't know. So does anyone else see the reference?
No, it's working fine on mine.
It's only for you.
Okay.
I can see them.
So let me take this opportunity to ask a question. So how are these pictures obtained? Is this what kind of model is that, or is this an observation?
So this is a theoretical description. So for example,
of what? A scalar wave or what?
No, it's an electromagnetic wave in the paraxial approximation, and it is circularly polarized.
Okay. Thank you.
Look at the 0,0 component of the energy momentum tensor in this plane.
Thank you.
Okay, so now let me continue and give you a brief summary of how we derived the equations of motion describing the spin Hall effect. So our approach is based on the WKB approximation. So we start with the WKB ansatz for the electromagnetic potential as shown here in equation 1, where we have the WKB expansion parameter epsilon. So for the sake of simplicity, we can roughly think of epsilon in this case as representing the wavelength. Okay. So now what we do is we take this ansatz and we plug it into Maxwell's equation and the Lorentz gauge condition. And this is what we obtain over here. So we obtain that the gradient of the phase represented here by P is null, and that P is orthogonal to the polarization vector A0, and also that the polarization vector A0 is parallelly propagated along P. Okay, so based on this orthogonality relation between A and P, it is convenient to rewrite the polarization vector in terms of a null tetrad. So we can write it in terms of vectors M bar, which are orthogonal to P, and also in terms of P over here, where Z1, Z2, and W are complex scalar components. Z1 and Z2 will describe the state of polarization of our WKB ansatz, and the component proportional to P is a pure gauge component which will not play any special role later on. Okay, but now in order to be able to fix M and M bar, we need to introduce some additional structure. So it is not enough to use just that A is orthogonal to P. We need to introduce either another null vector N or another time-like vector T. So in this sense, M and M bar will always be functions of P and the time-like vector T. Okay, so this is already anticipating to some extent the role of an external, of the choice of an external observer. Okay, so I'm going to skip the details and go directly to the final result, because this WKB ansatz would take us a lot of time. And what we obtain in the end are the equations of motion describing this gravitational spin Hall effect. Okay, so we have here the equation x dot and p dot, and if we look at the first terms over here, these are just the null geodesics equations. But on top of the terms which gives us null geodesics, we have some correction terms of order epsilon. So first order in wavelength, basically. Okay, and these correction terms depend on M bar, and also on our external choice of time-like vector field T. So basically, the correction terms will always depend on our choice of an external time-like vector field T. Okay. We also have another equation Z dot, where Z is a complex 2-vector. Basically, this is just another way of rewriting the parallel transport equation for the polarization vector in terms of what we call a Berry connection B. I'm not going to give the details of how B is defined because it's not really necessary for this talk. And also we have a constant of motion here, S, which is basically the helicity of our wave that we are considering. So we have S equal plus minus 1 for circularly polarized electromagnetic waves, and we have S equal plus minus 2 for circularly polarized gravitational waves. Okay.
So can one not just choose the vector t to be parallelly transported along P?
The choice of t is arbitrary.
Yes.
It just needs
to. So why not set this set the derivative of t with respect to P0?
So choosing a particular t is just a choice of family of observers which would describe the motion. So it doesn't make sense to pick one particular t as special. So there could be an observer which describes the same motion, and it would see it slightly differently. I'll try to show this with some pictures in the following slides.
I'm really perturbed by this. So this is, what does this equation of motion represent? The center of energy? Is this what's happening? Or, I mean,
yes,
when you have a wave packet, you need to say which part of the packet you want to describe.
Yes, exactly. So this will be, I think my examples that come in 2 slides will clarify.
Okay, thanks.
Okay. So before going to the examples, I have one more remark. So our equations can be put in a form which resembles the well-known Mathison-Papapetrou-Dixon equations. So in order to do this, we just need to define a spin tensor as over here, either in terms of m and m bar, or either directly in terms of p and our choice of external time-like vector field t. Then the equations can be rewritten as over here, where equation 9 and 10 represent the actual MPD equations, and the equation for x dot can be obtained from this MPD equations by imposing the spin condition S contracted with t equals 0. So in the language of MPD equation, the choice of time-like vector field t would to some extent fix our choice of energy center of the beam. Okay, so now let me go to an example, and hopefully this example will help clarify some of the things. So given the equations of motion, the most basic example that we can look at is Minkowski spacetime. So in Minkowski in particular, the equations simplify a bit. So we have basically geodesic equations plus a correction term over here in the x dot equation, which explicitly depends on the choice of external time-like vector field t. So now we can just make different choices for t and see what we obtain. The most obvious choice would be to choose t as the standard observer in Minkowski, in which case this second term is 0 and obtain null geodesics, regardless of the value of epsilon or s. The second possibility is to choose some family of boosted observers. So, and here I have t prime as one example, which is a family of boosted observers along the x-axis, where the rapidity of the boost is parameterized by the time coordinate in Minkowski. And in this case, the correction term over here is non-zero, and what we obtain are polarization-dependent trajectories. So let me plot you these trajectories, and hopefully this will start to make things a bit more clear. Okay, so the first choice of observer t, we just get null geodesics. So if we start here at the origin of Minkowski spacetime and we have a ray going initially along the z-axis, this will be a straight line in Minkowski. This is just the null geodesic that is seen by this family of observers over here. Okay, now on the other hand, if we look at solutions of the equations as seen by this other observer, t prime, which is the boosted observer in the x direction, then we see some polarization-dependent corrections. And instead of a geodesic, we see these different curves over here. And here we have a displacement between the the trajectory is seen by t and by t prime, which on one hand depends on the helicity, it depends on the wavelength, and then it depends on the magnitude of the boost of the observer. But as we see over here, delta y will be limited by the wavelength, so it cannot be greater than one wavelength in this case. So basically, what these equations are reproducing exactly this Wigner translation for Gaussian wave packets that I mentioned in the introduction. So the boosted observer will basically see the trajectory is slightly displaced as compared to the standard reference observer over here. Okay, so this is what happens in Minkowski. We can also look at a more complicated example. We can also look what happens in Schwarzschild, for example. And here we have the Schwarzschild metric, and we can pick two different observers in Schwarzschild and see what we get. The choices that I made over here are the following. So on one hand, let's say as a reference, I picked a static observer T, and as a second observer, I'm picking a free-falling observer T prime, given over here. And now I can take these two observers and plug them into the equations of motion and see what I get. And the result is, it's more complicated, obviously, but it's very similar to what happens in Minkowski. So with green, red, and blue, these are just the trajectories that I showed you in the introduction. Now we can compare this with the trajectories seen by the T prime, by the free-falling observer. And you can see here with the dashed lines are slightly displaced when compared to the solid lines. So this is basically a generalization of the Wigner translation that one sees in Minkowski to the case of the curved space-time. While in Minkowski, I was able to say that the displacement is always limited to one wavelength. Here in Schwarzschild, I'm doing a numerical simulation, and I'm not, at the time, I'm not able to say this analytically, that the displacement is still limited to one wavelength, but this seems to be the case nonetheless. Okay, so let me conclude my talk. So we provided a covariant framework for describing the spin Hall effect, as well as the observer dependence of the position of massless spinning particles. So our equations of motion reproduce the effect of the Wigner translation in Minkowski, and they also provide a generalization for this effect in curved spacetime. Okay, so now with this theoretical framework in mind, what we aim to do is to focus on astrophysical applications to see what are the implications of our equations for various applications, such as gravitational lensing, black hole shadows, or wave optics phenomena in astronomy, for example. These are just a few examples. One can go beyond this list. Another interesting possibility, which would involve experiments on Earth, would be the following. Are Wigner translations experimentally observable? Even though this is a sub-wavelength effect, weak quantum measurements, for example, can in principle detect such displacements, and this might be a possibility. Okay, thank you very much for your attention, and I'm looking forward to any questions.
Well, thank you very much for this clear talk. Well, just one very quick question. So the necessity of introducing this observer is related to the massless nature of Maxwell field, right?
Yes, exactly.
Okay. Any more questions or remarks?
Bobby, there's a question from Gautam from the audience.
Yeah, can you hear me?
Yeah.
Yes.
Okay, so first, are your equations exactly equivalent to the Majumder-Papapetrou equations? Is there no, I mean, and then second, I mean, I think you did mention this on a slide, so I may have just missed a particular point, but those equations require this spin supplementary condition that you had before. Is that derived from your, WKB type approximation, or is, okay, I see.
Yeah, so we're doing the WKB, we're deriving the equations over here that you see in 4, 5, and 6.
Right.
And by just rearranging the terms afterwards and defining the spin tensor as over here, we obtain this form of the equation, 8, 9, 10.
Is this form of the spin tensor the most generic form of the spin tensor that you could write down from the Majumder-Papapetrou, or is this a specific kind of, spin tensor that, that is coming from your analysis?
No, this is coming from our analysis. And then we just observe that equations 8, 9, 10, which are our equations, are equivalent to the MPD equations with this supplementary condition, S contracted with T equals 0.
Thank you.
Okay,
so there's a question from Thomas also.
Yeah.
Yes, so I would like to know whether you can somehow assess the quality of your WKB expansions, because I'm aware of some analysis, at least, which says that the standard WKB expansion without spin effects for just iconal equation and transport equation for the amplitude are at least asymptotic solutions to Maxwell equations in certain cases. Can you say similar statements about these spin-dependent expansions?
At the time, I can only make speculations. So we didn't made any quantitative assessments of this. But I can only speculate. But that by including higher order correction terms, you improve the limit of validity of your model.
Okay, thanks.
May I just make a comment on the supplementary condition? As far as I understand it, I mean, this simply states that there's only spin present and, so to say, no boost component in S for the observer T.
Yes, yes.
Okay. Well, I think, yes, we can now move on to the last talk. By Martin Lesur. Are you here? Oh, hello.
Hi.
Welcome.
Thank you.
Okay.
You can see my screen?
Yes. So this is now the third talk of this afternoon's, of the second half of this afternoon session, which is given by Martin Lesur from Harvard University, Black Hole Initiative, on the construction towards the formation of black holes. Please.
Thank you very much for the opportunity to speak. I spoke at this meeting way back in 2018, and that was a great time. So I'm very happy to be back, although I would like to be in Vienna in person, of course. That's not possible right now. So this is based on joint work with Nikos Athanasiou, who's at Imperial now. This was done when he was still at Oxford and I was too. And we'll be talking about some work which is a paper on the archive which you can find. So I'm not going to bore you with the most kind of elementary slide. I'm sure you're all very familiar with this. Of course, I won't be dealing with any matter here. So the constraint equations will just be the ones in vacuum where T is 0, and we're in n equals 3, so space-time dimension n equals 4. So these are my equations, and we'll be talking about black hole formation. Now, what do we actually know about black hole formation? Well, in spherical symmetry, there are, of course, the 1939 Oppenheimer-Schneider spherically symmetric. We have the dust models. And in the context of a scalar field, we have the work of Christodoulou, which spans the 1990s, where we have a pretty good understanding of what happens in that context. And that's both with respect to black hole formation, to some extent, weak cosmic censorship, and so on. But of course, more generally, we want to know how do black holes form dynamically without these assumptions of spherical symmetry. We'd like to know that when they form, do they actually asymptote to model solutions in the context of vacuum? Of course, that's important for astrophysics. In astrophysics, most of the time, people superimpose things like the angular momentum or the mass or the radius on the observations, and that's only valid if the real astrophysical system is a good approximator or approximates these model solutions. And then, of course, this question of black hole interiors is much more like Schwarzschild. Well, are the interiors more like Schwarzschild or Kerr? Namely, what's the nature of the singularity inside, or is there a Cauchy horizon, etc.? That's strong cosmic censorship, so we won't be talking about that. But that's another question you could ask about black holes, and especially the astrophysically relevant ones. So these are the you could argue the big five in the context of vacuum. You know, the big five conjectures you might wish to make. So, I mean, one is kind of obvious to see what this is saying. So Kerr stability, right? You had an initial data set for the Kerr exterior. You perturb that initial data. Does it still produce a Cauchy development, which is like Kerr? Right? So does it asymptote back to Kerr? Strong cosmic censorship we won't be talking about, but essentially you could think of it as the conjecture whether or not the Cauchy horizon is stable under perturbations. Rigidity is whether stationary vacuum black hole solutions belong to the Kerr family. Weak cosmic censorship, generically, you know, is the maximal future development of vacuum initial data. Does it lead to something that's globally qualitatively like Kerr? So is there a complete scry? Is there an event horizon, etc.? And the final state conjecture is kind of wraps up all these conjectures together and asked whether the vacuum development of initial data that leads to trapped surfaces, say, does that actually lead to a black hole spacetime, which in particular looks like Kerr? So not just qualitatively, so with regards to its global causal structure, but actually quantitatively. So is the geometry approaching Kerr? Right. So these are some of the big, very, very big problems that are all kind of open. And the first route towards, it's a long road to these problems, but the first kind of dynamical formation result is Christodoulou's result. So again, this is for the Einstein vacuum. We have short pulse data, which looks like this. So this is the traceless part of the null second fundamental form on the outgoing null cone. And so this is saying this is a small parameter. There's this annoying setting which I must get rid of. And this is saying that essentially, you know, you will have, so this part is the existence part, right? The existence theorem. And this tells you that if your data looks like this, right, then you get a solution to reach E0, at least in this region. Okay, and what's amazing about this result is that it's a balancing act between having initial data that's sufficiently large that you can eventually form trapped surfaces in the second part of the theorem, but that's sufficiently good that you can actually prove an existence theorem, right? And that's the whole balance of the proof. That's the whole difficulty of the proof. You need to construct initial data that you can actually solve, right, in the sense of evolution, but it needs to be initial data that allows quantities to grow large. In particular, this infimum is over the angles on the initial sphere. So my angular parameter varies along the initial sphere, and then it's transported along the outgoing null cone. So this is saying that, you know, if the integral from 0 to delta of the shear, so again the traceless part of the null second fundamental form, if that's sufficiently large, then again after picking your delta sufficiently small, then the sphere at the top of the diagram is trapped, right? So this is a dynamical formation of trapped surfaces result. It was the first one of its kind, and It was the first time that people had initial data that didn't contain trapped surfaces, but which in evolution led to the formation of trapped surfaces. And there's no symmetry assumptions here at all. It's just initial data. So in 2012, Li Yu put a paper on the archive, which eventually was published in 2015 in the Annals of Mathematics, where essentially what they did was take the result of Christodoulou and use the Corvino-Shane gluing arguments to add on a Kerr slice onto the slab, the space-time slab of Christodoulou. And there is an interpolating region where the space-time is under control in some sense, at least for a sufficiently small square. But the point is that you construct a Cauchy initial data set where there are no trapped surfaces on this initial data set, but the future development of this initial data set has a trapped surface. So it's a translation from a characteristic initial value problem to a Cauchy initial problem for the formation of trapped surfaces. And what you get is that you get a concentric structure. So the first, the center, if you like, of your initial data set, so this is diffeomorphic to a ball, is a constant time slice in Minkowski. Then at the, out in infinity, you're isometric to a slice that embeds in Kerr with m close to m0 and small angular momentum in this way. And in between, you have this interpolating region. So this is the theorem of Li Yu. This out here is Kerr, and this is the Christodoulou slab. So these are the pulses of radiation that are sent, right? This sphere up here is trapped. This is the space-time slab that I told you that was under control. This is Minkowski. And you get a portion of null infinity because, of course, this is Kerr. If this is Kerr, then you get a portion of null infinity, but you don't get the full null infinity. In particular, you don't know what happens in this region up here. So this region you don't know, and although you know that this sphere is trapped, you don't know anything about the trapped region. You don't know anything about marginally out of trapped surface. You don't know anything about an event horizon. You don't know anything about the geometry in future infinity or future time like infinity. So it's a good step, but it's certainly not a full black hole result because you haven't continued the space time. So this is the background result, and let's keep this in mind as we go forwards. So Anne Luc refined Christodoulou's result by basically having milder data. So you see, before we had a delta appearing here, and right with the shear was here, and we had an extra derivative inside, and we had a delta appearing here. So this is saying, when you have this type of initial data, this is essentially saying that the shear is smaller, right? There's not as much shear. So it's milder data, but it's still strong enough, as in it's still large enough in that you can actually produce trapped surfaces. And part of the value of this improvement of their result is that you can actually understand the size of the initial data that you need to have in order to form trapped surface. In particular, you relate that in terms of parameters related to the region of existence and the size of the initial data. So in Christodoulou's result, you had no control over this. You just had a region, and you just said, right, if you crank up the initial data, and if delta is taken sufficiently small, then you get a trapped surface. This is quantitative. This is saying, if the initial data is like this, then I need to choose my delta like this. And if I have a parameter A and B like that, then everything works. So you can think of it as a kind of quantitative version of Christodoulou's result because of this precise dependence on the parameters. So this is what this slide is saying, right? In the Christodoulou result, you just have to pick delta sufficiently small. You have no idea how big delta needs to be. Whereas here, the size of delta is pinpointed in terms of the other constants relevant in the problem, other parameters, right? In particular, delta appears here in the size of the shear that you need. So for instance, if you fix your delta like this, then you actually recover Christodoulou's theorem, but you have the added bonus of having an even larger existence region. So this is definitely a very interesting result, which kind of refines Christodoulou's formation. And so now I'm getting to the current work. How am I doing for time, by the way? Do I have about 10 minutes left? Hello?
Bobby, are you still there?
Yes. You have a few minutes left. Yeah, you started only at 4.
Right. Okay. Good. So the basic idea is to do the same trick as Liu, construct the Cauchy data, but do it from this improved result. Right. That's the basic idea. So this is a slide that explains this. So we construct Cauchy data for the formation of an apparent horizon, not just a single trap surface. And in that sense, you kind of obtain the scale critical version of Liu, where the later is kind of morally obtained as a corollary from the former, right? So it's like a refinement, right? Now, what's interesting is that you can pinpoint the size of everything, how big delta needs to be, how big A needs to be, B, etc., all the parameters. And from the point of view of general relativity and formation of black holes, you actually get a lot more. So you get a trapped region bounded by an apparent horizon rather than a single trapped surface, which was what you got from Christodoulou or Liu. And then modulo the enormous work going to Kerr stability, which, granted is not proven yet, you actually get a class of conditional examples to weak cosmic censorship in final state, which is different from Liu's, because you have different estimates for this milder data, which in particular allows for a weaker statement that you need to use of Kerr stability in order to complete your spacetimes and to go all the way up to future time like infinity. And then the final bonus is that you actually, because of this milder data and this extra control you can get on everything, you actually obtain area estimates for the marginally outer trapped surfaces that foliate the apparent horizon. And what that means is that you can actually see the apparent horizon growing, right? So you can actually think about Penrose's inequality now, and you can give a dynamical setup, a dynamical kind of, scenario in which you can verify and see what happens to Penrose's inequality in a dynamical setting, right? Which is new. So what does the initial data look like? I was going to bore you with this, but actually with time running on, I'd rather show you a diagram. In short, you have to add an extra delta, but it's still critical in the sense of Van Luke. So there was an extra power in Christodoulou's result. There's an extra delta to the half that we don't have. You have to kind of assume this, this condition which says that once you've integrated up to delta, then there's no angular dependence on the shear. So this is nothing like spherical symmetry. It's just saying that after you've integrated along all the directions, you actually get something that's independent of theta, which is the right angular parameter on the initial sphere. And then you have to kind of modulate your initial data carefully. In particular, you have to kind of interpolate between a linear dependence in U bar of the integral of the shear and a constant value. And this is what this condition is doing. And that comes from Anne's work. I mean, it's not in Anne's work, but we had to, in order to build an apparent horizon, in order to have marginally outer trapped surfaces as opposed to trapped regions, or as opposed to a single trapped surface, you need to control the data a lot more. So this is the first theorem. I mean, I'm not gonna bore you with speaking and I'm just gonna show you a picture. So this is what the theorem says. The theorem says you send in a pulse of radiation, you form an apparent horizon. So here so this is a tube, if you like, that's foliated by marginally outer trapped surfaces. You get this trapped region full of trapped surfaces, and you get this extra region, and you kind of have these estimates for all the relevant quantities in this apparent horizon. You can even see the apparent horizon tending to something null, right? So the well-known idea that apparent horizons tend to event horizons, you can kind of see that at a semi-global level. I mean, you don't have an event horizon here, but at a semi-global level. And then this is the Cauchy initial data statement. So you have your parameters in the interpolating region, you have the concentric structure on the initial data set, You have some quantitative control over how big epsilon needs to be, how big delta needs to be, etc., which are things that you couldn't have had before. And this is the theorem. So the theorem says, you send in a pulse of radiation, then you stop the radiation along this hypersurface, then you get an apparent horizon, you get area estimates. Let's zoom in. You get area estimates for the MOTS that foliate this region. So that because of the gluing now, because of the Kerr, N with the controlled ADM mass and angular momentum, you can now test the Penrose inequality on these kinds of slices. You can see the Penrose inequality actually being proven dynamically in the course of evolution. You get some estimates and some control on this region here. Let me change the whoops. There we go. And then you get, in particular, you get estimates here for the quantities, which look like this. So all the left-hand sides here are with respect to M0, and that's a Schwarzschild space-time of mass M0. So all the quantities here are with respect to a Schwarzschild space-time, and then all the right-hand sides have a delta or a delta to the half or U's, etc., which tell you how big these things. But with this extra control, you can find out, what's the way, how do I make these estimates as small as I can? And for that, you choose your parameters wisely, and you can show that everything here on the right-hand side depends on C, constant independent of delta times delta. So essentially, they can be made as small as you like, choosing delta as small as you like. So that's how that works. So this is what this slide is saying. Express everything in terms of delta or A or B. This is the extra parameter freedom that is allowed to you by the quantitative version of Christodoulou's result, which you didn't have before, and that came from Anne-Luc. The worst estimate is like this. The MOTS is located here. So, evaluating this, you get something like this, and then you want to make this C as big as you can. A is a large constant, and so you end up getting with estimates that look like this, where C is independent of delta. This C is not the same as this C. And that means that essentially you can make the initial data as small as you like, so as close as you like to Schwarzschild or Kerr, and that means the stability result will carry you all the way up to future time, like infinity. The Penrose inequality, there's my last slide. The Penrose inequality, well, here the area estimates, right, for the relevant quantity appearing in the Penrose inequality is kind of linear in U bar and looks like this in terms of the other parameters. And you get an equation for M0, which is the thing you eventually glue to. And then the ADM mass of your Kerr end is close to M0 in a particular sense. And so if you want to test the Penrose inequality dynamically, what you do is, you take the relevant, left-hand side of the Penrose inequality, the thing that needs to be larger than 0. You have estimates for the mass, you have estimates for the area of the MOTS, and so you can start understanding what this term is doing. And what you get is this. And then you can evaluate the inequality here, and you can choose your parameters once again, fix all your parameters to try and make this greater than 0. And you get that you can prove it, right? So after choosing suitably your parameters in a way that consistent with the initial data, you eventually prove that this is true for the MOTS appearing in your dynamically created apparent horizon. All right, well, I should probably stop there then. Thank you.
Thank you very much for a very interesting talk. Now, we can still have a few questions. We're running over time, but it's the last talk. So, anybody?
So, Martin, your space-time at the end is Kerr or is it Schwarzschild?
So out here it's Kerr, and then here it's a perturbation of Schwarzschild, and then here.
But Kerr is of course a perturbation of Schwarzschild. So yeah. Maybe the question is, does it have angular momentum or something like that?
Yeah, it has angular momentum, but the angular momentum is small.
Thanks.
Yeah. But it could be 0, couldn't it? Or not?
No, it's not going to be 0 because to kill the kernel in the gluing problems, to kill the kernel, you need some leeway in the, because you need some, like, there could be angular momentum in this initial data. You could try and fix the angular momentum to be 0, but I don't know how to do that in terms of the initial data. So you could fix that, and maybe you can try and glue to Schwarzschild, but I don't know how to do that because that would involve expressing the angular momentum in terms of this initial data here, but this initial data here is already very constrained by the problem, by everything, by trying to control everything. So you have this extra angular freedom, which leads to some angular momentum, which appears when you try and kill the kernel later on to do the gluing.
Awesome. Anything else?
So in this drawing, the spacetime is really defined to the future of this light cone and this space asymptotic flat space-like surface, right?
Yeah. So the spacetime, the portion of the spacetime that's missing, and that would be given if Kerr stability was known, would be everything up here.
But what about to the past?
Well, to the past, you'd have to, well, to the past is a good question. What you'd have to do is, well, so we haven't extended this all the way back to past null infinity, but in principle, that's doable. But that would be harder because then you'd have to control a larger portion of the spacetime. In particular, you'd have to control what happens here. And we also don't know how to do that because that, you know, that region now, this gray region here is close to a Schwarzschild black hole. So proving something about here is close to stability of Schwarzschild. And so in other words, we don't know, you know, in other words, the past is not known. But
we know the future.
if Kerr stability works, yeah. Yeah.
So, there doesn't seem to be any more questions or remarks. So let's thank Martin again and all the speakers of this session. And goodbye until tomorrow.
Yes, so see you tomorrow around 10, I believe, right?
Yeah.
Bye-bye. Thank you very much.
All right. Thank you.
Bye-bye.
Bye-bye.
Bye.
Bye.
Thomas, what do we do with the streaming and with the recording? Do I need to become host again and
presumably, but
stop
let me
things?
try. I can stop the streaming as well.